also shows that they care about the heritage, and they want to include it as early as possible. So, and also they can develop an earlier and more fruitful collaboration with ground owners, because then you can, to a certain degree, evaluate if there's any conflict on their land without ruining the crops or digging up the ground. So for them it has value outside of just what they're obligated to do, and they don't mind paying for that, you could claim. Also, the results from geophysical surveys have value outside of archaeology as such, and I'll come back to that later on, but I can mention it quickly, and that is like for geological mapping, drainage, ditches, and all these things that often is poorly mapped, or you don't know where you put exactly where you put the ditch last year. You have a map maybe, but that was just someone drawing a line. Things like this. I'll come back to that. But the consequences of, you could say, kind of the somewhat a bit lack of the usage of geophysical method, if you want to talk about that, you can say, I said political versus knowledge-based management, that decisions comes from top down, or not from necessarily researchers that can have the say. There's been a slow implementation on conventions, treaties, and strategies, and that's interesting. For the Valletta Convention, for instance, says that you should use non-intrusive methods whenever possible, and that's a convention that we've signed, that we in Norway at least are supposed to aim for as the goal. And then you can discuss what is meant by non-intrusiveness, and this is written before people started to talk about preventive archaeology and such. I think it's mainly written to kind of enhance develop a PAES principle. Treaties, there's the ICOMOS treaty and things like this that also mention the use of non-intrusive methods. So this is something we've said we should do, but don't necessarily do. And I would say that there's less focus on the values of preservation, knowledge, identity of cultural heritage management. And there's more focus on holding costs down and avoid negative press. So the value of the heritage itself and its meaning to the locals is kind of hold down a bit, and a lot of the management people often just want to kind of hold the costs down so it's not too costly. I forgot what was next.
Okay, it's recording now.
Okay. I had such a long break, so now it's not jumping to the next image. There we go. This is the radiometer data from the same site where you have the furnaces. It turns up like that. And then you have the central part of the slag mount. What we didn't see, where you see so partly as something that looked like a wall, was actually this round thing, which was really, really highly magnetic. And then these blobs, which is probably where you prepared the iron ore. This was probably the storage. You prepare the iron ore, you store it there, and then you toss it into the furnaces. That's our interpretation of that, at least. So at least we can start to distinguish and find areas. It's also important because usually what was protected was the furnaces and the slag heaps that you found. But it turns out that the activity area extends at least somewhere between 20 and 30 meters into the terrace where the iron production was. And that's interesting because if someone of our colleagues go out and find one of these, they should also put the border to the monument at least 30 meters behind the edge of the terrace to make sure that you catch those things as well. This is another site, smaller, 2 slag heaps, and some of these, analyze them in detail, looks like furnaces, and then you also have those small little hot spots that's a bit away from the air. This is probably where you roasted iron ore. So the challenge then, you could say that the technology is a new way for us to sense archaeology or see archaeology. So you move from data to some form of interpretation of that data, and then put this sign in to say, is that really a archaeology or archaeological? So this is just data. It doesn't make sense in itself unless you know how to interpret it, and then you try and translate that into some form of archaeological interpretation. That's the difficult bit. And a guy said that no object, Dag Myklebust is an archaeologist, I think, and also a philosopher, and he said no object is cultural heritage, or a cultural heritage object, until it's sensed and interpreted as such. So you could claim that detecting or using geophysical methods and non-intrusive methods to detect anomalies into the ground is a different way of seeing archaeology. You're not seeing it with your bare eyes, but you're seeing it through a machine. And what is really the difference, you could claim? Of course, the die-hard digging archaeologists say, oh, well, you don't know what it is until you've seen it with your bare hands. And sometimes you get geophysical results that shows things quite clearly, which is barely or not even visible with your eyes when you're down there trying to look into the ground. And a good way of exemplifying this is these two things. They kind of have the same appearance, strongly magnetic with a negative halo around it, and also strongly magnetic with a negative halo. That is an Iron Age furnace, but that is just a very magnetic stone. And how do you distinguish between those two? Not archaeology, that is archaeology, and that's protected by law. So you can try and discuss, well, how is a cultural heritage object defined? You don't often get a letter of authenticity together with it, or who decides what is considered to be a cultural heritage object? Who is it that in the end says, yeah, I think this is old and archaeologically important, and I think that's not so much. Some people sit down and write guidelines on how you should do it. Sometimes you have some professor with a strong academic background who should know what he's talking about, and when he says it's that, then it's that, and you can't discuss it anymore. So certain people have, of course, more knowledge into something, and their word or their interpretation of it carries more strength. And then you can come with your goddamn guidelines and it won't really help you. So I call this the challenge of the interpreter. This is the same two things. So they look kind of the same, but when you see the area of the positive, these are all the things that turn out to be rocks from this particular survey. It's a plough field with iron furnaces in it, and one of them has it's under 2 square meters, but all the other ones that turn out to be rocks are about 3 meters in the area, while the furnaces are all under 3 square meters in area. So if you'd known that from beforehand, then you interpreted everything above 3 meters as probably a natural thing, and everything underneath as archaeological, and then our interpretation would be a lot better. And we didn't know this before this was done, but that's something we learned by looking at the excavation data afterwards. This is actually going to be published in March or April as an article in the Norwegian media. There's this, back to our example, here's a GPR profile. I think it's migrated, so it's more focused than raw data is, but you have those pit-like things. And well, yeah, it kind of looked like a pit in plan view, in profile, I mean, in the section. And then you look at the plan view of that particular thing and you start to see, oh, more stuff. And those pits, some are deeper, some had some very strong reflections in the bottom of it, like this one as well. And well, can look like something, but without context. It's actually this line through the mound with through the house with That's a roof bearing post. That's probably a roof bearing post and a wall post. No, actually, that's a wall post, and that's a pit outside of it, and that's the roof bearing post. And this big one is out. So it's only when you start to look at the bigger picture that you actually understand that this dip in a section is actually part of an archaeological context. So sometimes you can do very good geophysics in very focused areas. It's not always a question of area and size and coverage. It's depending on what your aims and objectives are. But sometimes also what really is starting to give results, and also what's changed the use of geophysics in Norwegian archaeology is our ability to cover really large areas. And then it's the challenge of the receiver. In that, I mean, you have the specialist collecting and interpreting the data, and then you have that report is sent to someone who then has to decide what to do with it. So for it to have a best possible impact or use as such, or be more useful, it's important, I believe, that the receivers of such a geophysical report must have some form of, doesn't have to be experts, but have some form of knowledge at least on the potential and limitation of the different geophysical methods, and also a reasonable expectation of what you can achieve with a geophysical survey. And also, and this is maybe even more difficult, is than when the challenge is to start to weigh values against each other. How much ship that went down? I can move over here so you can see.
No.
If it was a ship that went down with its cargo, the cargo is probably part of a ship. It would be a very inclined and it's protected. But if someone tossed that flask from the shore and it ended up in the water, it would be coming from land, and therefore it wouldn't have a protection. So just setting like some form of year or age to decide what is considered archaeological or not, it could be beneficial, and I'd see from a legal perspective it might have some value, but maybe a more fluid attitude to it. But then again, then you'll end up with some very, I would say, probably quite individual, reflecting people's individual interest in what they care more for or think is more interesting than others, and that could be a problem again. So, but from geophysics point of view, then you can say, well, is this blob older than 1537? Sometimes you can't say that, but that blob is part of something you recognize as either a ring ditch for a burial mound or a post hole, obviously from a house. Then you can start to say it. And from a Norwegian perspective, it's not me as a geophysical practitioner who says that. I can present my interpretation of it, but it's someone else who decides whether or not they believe in my interpretation and decides on the legal implications. And in Norway, it's the county archaeologists that has a connection. And I'm not sure how it's built up in Finland, but someone who probably has that responsibility to decide whether or not this is considered archaeological or not. And that requires that you actually have to read a bit of law and then see how things are defined legally to find out who it is that decides whether or not something is considered archaeological.
May I ask one thing concerning this discussion? Let's say that you have a house remains from the late 16th century.
Yep.
Yeah, let's say we have a house remains that are probably from end of 16th century, and then it turns out that it is from the early 16th century. So what is the difference then, what you can do or what you have to do if it's archaeological, if it's not archaeological find? What are the laws that are
Well,
like protecting this.
if it's newer than 1537, it doesn't have a legal protection. But you
It
can,
doesn't have at all a legal
If
protection.
it's new, no. But someone can say that it has if it's deemed important enough.
Yeah, so you have to explain it.
Individual treatment of it, and you can give something that's more recent a legal protection if it's decided to be important enough.
Yeah, that's very interesting. Really, that.
Well, I'm not sure if that got your question.
Yeah, you did, because that's what I wanted to know. That is there a protection for this younger than
automatic protection.
1537?
1537, it's a standing building. It's also
Yeah, but not automatic or
but if it's more
heritage
recent, it could be,
protection.
Let's say an area of very of a particular activity. Let's say it could be a prisoner of war camp, for instance, from Second World War or First World War or whatever. That doesn't necessarily have a legal protection, but it can be given one if it's decided that this is so important to keep or to study or to understand. Same with, like, say, the mining town of Røros. All the activity there started after 1650, but there was a lot of very, and of course antiquarians working with buildings, this is important, and they can go in and but the town of Røros, then they decided that there's so much history and so much archaeology there that you can't do anything in the ground without having archaeologists coming and monitoring any dug activity there, because the whole town started after this legal date.
So how is it if you have your house or a farmhouse in the area where there was early historical activities? So can you just do whatever you want if it's not older than
farmland? You can, unless there's been imposed particular restrictions, you can plow and farm your land as you always have. That's within the Norwegian Cultural Heritage Act. But if you notice something that is archaeological, or you think is archaeological, you're required by law to stop and notice the agencies. That doesn't mean that they do, but legally
you have
should
to
stop the
announce,
activity and announce it, and then they should send a representative to come and visit the site and decide what to do next. And of course there are various schemes to fund, if it's a smaller private activity or building scheme, then let's say you're expanding your bar. Where we compare, not at this site, but where we compare the results from typical slow stripping site evaluation in large scale GPR, and then compare that with the excavation results, because we wanted to evaluate not only how well does geophysics work, or how good are our interpretations of geophysics, but also, well, how good does the test crunching, for instance, work. This way of doing it, I'm not sure how usual it is in Finland. You do a bit maybe. This is a Norwegian study, and it's probably studied in Denmark and a lot in Sweden and a lot of other places. You do strips, 3, 4, 5 meters wide, and then you cover about somewhere between 10 and 25% of the area, and you see what you find in the strips. And then this vastly changed Norwegian archaeology from the middle 1990s and then onwards, and it led to a completely different understanding of especially Iron Age settlement sites, because suddenly we didn't find them. We started to do this especially in plowed land, but also in forests. You can do it. It's more difficult, but it can be done. And we started to find a lot of settlement sites that we didn't see before. This really changed it all, from having barely no settlement sites to having them everywhere.
When was it introduced to Norway?
Right mid-90s, and it took about 8 to 10 years before it became standard practice. Now it's the first to come, especially for Iron Age evaluations. If it's Stone Age, you can try this way, but then it's test pitting. That's the most standard way of doing site evaluations. This is the usual way. It's a destructive thing. Some can claim that this might be a little overdoing it. There's quite a lot of them going on, and I've seen the worst example I've seen is where the test trench over 30% of the site. I mean, basically they partly excavated 30%. There's an article published by in the Netherlands or by some Dutch researchers that says if it's a site with a very high frequency of objects or features in the ground, 5% is enough. If it's a low frequency, 10% should do it. The standard in Norway is usually more, but it's kind of up to usually a very it could be a very well experienced one. It could be a master student. It could be who knows. It's up to them to decide where they put the trenches. But of course, local knowledge on, let's say, wind direction and topography and whatnot is usually quite important. And often it turns out like very small little, it could be like 20, 30 centimeters small little high rises. This is where we find the houses, for instance. Usually on well-drained soils. But it can lead to situations like this. The green area is the area that we covered with the radar. These ones are the test trenches by the county. And all the blobs here are the excavation results. They just missed these. It couldn't be more unlucky than that. And of course, this is almost the only pair of trenches where the distance is slightly more than the rest. The house is there, it's just in between two trenches, and sometimes you just really unlucky. And the reason why they opened this in the excavation was because I noticed some of these pits in the GPR, and they were about to open the area, and I said, it would be really cool if you opened that up, and they found the only house in that excavation. This is how it looks in that depth slice, and then you have these are cooking pits. It has that little very white, black speckled response that we often see when you have a gathering of stones. It was like 10, 15 centimeters deep, and they're probably not burials, they're probably some form of, what do you call it, for drying grass, I think. You had a pole in the middle, you had a dish around to drain the area, and then you pile the grass up with like spikes, and that was used to dry crops or grass. And these are the excavated features. The blue ones are, well, the purple ones are the ones that were visible in the radar. The blue ones we didn't see with the radar. Especially the small ones here and some other ones. They were part of the interpretation. And these are some features that are found in the trenches. And you can see those features that were drawn into the trench was not excavated, or were not found by the excavation. So these are the detection rate of the trial trenching versus the excavation, where you see they found like 83% of all the cooking pits. They found 26% of all the post holes that were excavated, of the pits and so on. A total of 29% of all features found in the excavation, where you have time and you covered the whole area. You see more when you have a large area covered than just 5 meters. Of course, if you have a series of posts and you're lacking one in the middle where it's supposed to be a post hole, you can use it over time, clean it properly, and it might show up. You usually don't have to do that, time to do that when you're at test trenching. When you look at radar, for instance, you can see there's like 69% of the cooking pits was visible and interpreted which is that there's not that much of a difference. Actually, when you look at the post holes, and this is not ordinary, that you see the same percentage of the post holes in the radar data as doing test trenching. Usually it's less, but this was with the housing between that they just missed. And a total of 23% of all the features found in the excavations were visible in the data. So you don't find anything, but neither do you with test trenching. That was the whole point. The advantage of this is that you have a visual expression, you recognize things, you might excavate a few features to be sure what they are, and you can do datings. You can't date the geophysical expression, but if it's a feature that you recognize the shape of, you can do it typologically. We did another thing, we did density modeling of the features detected by radar, detected by trial trenching, and density of the features that were excavated, and then we compared those at two different sites. This is the EA site. The trial trenching results didn't really correspond very well. This is the spatial correlation, statistical correlation between that, and the spatial correlation between that and that was only actually 0.50%. I double checked, sorry, triple checked that number because it sounded so weird. For the data that we initially interpreted, one thing is what we interpreted, and nothing was what was actually visible. For what we interpreted, it was 0.45 correlation, but for what was actually visible, it was very good correlation between that and what was found in excavation. In Dilling, the trial trenching had a better correlation, and also the interpreted data, but also that. So that means that although we don't find anything, the spatial representation of the site is comparable. This is better than radar, while at AI it was actually better with the radar compared to the test trenching. So that means that even though we know that we won't find anything, the spatial representation of what we find equals the sites themselves on Iron Age settlement sites. So that's something we can carry on with us when we are out and about and doing this. And it's back to the additional value that you can get a different impression of the geology. Like here, for instance, at AI again, you see some paleo channels, the old river channel that's on there. This white bit is actually more silty soil from a landslide. There's probably another quite wide paleo channel, this bit. And also, drainage ditches, the whole series of them, so we can present the farmer with proper maps of where the drainage ditches are also. And of course, if there's like pipes and cables and things like this, that could be an obstruction, we can find them. To try and sum up a bit about the status in Norway, there's you can say a discrepancy between the convention and the strategies, especially on the European level, and the actual daily practice in Norwegian archaeology. Geophysics is not part of the daily methodological considerations. If you ask the directorate and their guidelines, geophysics isn't mentioned, but it's not mentioned as the main method of surveying, but something that can be considered if the developer agrees to it. Which also is a bit strange from a legal perspective, because should the developer then tell the archaeologist how you should find the archaeology? That doesn't really make sense, and also not from a legal perspective. Also there's some misunderstandings, because it's often described as new and untested, but it's not necessarily new. Actually, we can show from the graph I showed you that we've been doing this for quite a while. And it's only the previous problem is that the researchers or the people in position to do that kind of take those kind of decisions haven't necessarily read those articles, seen those reports, or caught up with the recent developments. Therefore, it's not necessarily untested either. Then what we often are faced with is like people claim that it's not tested on Norwegian archaeology, but I can show you, when people say that, I can show you like 15 examples of magnetics or iron production sites from Britain, so why isn't that good enough? Well, we have to test it on our own archaeology before we can believe it. Alright, someone has to go out and do it, yes, or something for that sake. So we have more knowledge on the possibilities and limitations. We know more on the effect various geologies have on our data sets. What can we do radar on clay? Well, yeah, we can do radar on some types of clay, but not necessarily marine blue clay. Clay is not clay as such. So it depends on the contrast between the feature, what it's dug into, and how deep it is. What's the accuracy of your methods, what's the potential of your methods, and what really changed geophysics in Norway is acceptance there is our ability to do large areas with high resolution. Then we're talking sometimes even landscape scale. So the biggest surveys I've done is about 10 hectares. But my colleagues at NICU have done projects with 50, 60 hectares in relation to road developments. And as I said, now the latest tender that I put out is 150 hectares. We don't know who gets that yet. And also that the knowledge that we have on all these things, accuracy, potential, limitations, and all that has to be passed on to what I call actors within archaeological research and management. And there's various ways you can do that. You can do it like this, ask questions, get someone to come and talk about it. You can go and do training, the cost action, which is the reason why I'm here. It's a European network that is encouraging and do training schools to train and learn various techniques and also look at relationship between the geophysical results and the soil parameters, for instance. Or write it in your research projects. Try and do some basic testing to try and find good ways to answer your research questions and see if any methods like this could be a good thing for your project. That's my conclusion. Let's see. Yeah, that was it. I'm happy to answer any of your questions if you have any more. I can show you more data if you want to see other examples, or come with recommendations of articles or any like sources if you need more information on whatever it is that you are working with. My email address is very nice to find. I didn't write it up here, sorry about that, but it's Arne Stamnes. If you type that in and anything, you will find me very easily.
Thank you.
Thank you very much, Arne. I'm sure that we will have some questions now for you. Kalle is ready.
Hi. Being a maritime archaeologist, I'll ask, I know that ground penetrating radar has been used in freshwater sites and saltwater. With saltwater it doesn't work, if I'm right, or there are problems.
In theory, not unless it's very, very powerful.
Okay.
Usually not allowed to do that on those situations. But yeah, GPR, electromagnetic techniques, salt is a bit of a problem. That's why it's not necessarily good for saltwater, but fresh water, it's almost like bottom penetrating
Sub-bottom profile.
Sub-bottom profile.
Yeah.
But maybe potentially better resolution if you do it in the right way.
Great, because that was going to be one of my questions, but you already answered that. But
yeah, we have a wreck in a freshwater lake, and it's about 8 meters deep. And we wanted to go and survey it on ice with this thing. The problem is that we have quite a crappy winter, so the ice isn't strong enough, so we just have to wait. We don't dare to go out there right now, but there is a few examples of at least sections through it, or people putting a GPS antenna on the bottom of a flat boat and dragging it over across a river or something, and it works. And you can do it to say what's the depth of it and what's does the sun bottom look like. And of course you can combine that with a lot of other marine techniques. You can also do magnetometry, marine magnetometry, or side sound sonar, or whatever it is that you want to do.
And that sounds really interesting. I've been talking with Vesa, of course, for years, but I'm doing research on in southern Estonia in a small lake where they have a pile dwelling, and I've been throwing into the site, if you want to put it that way, a lot of techniques, side scan sonaring and also photogrammetry. Sorry?
How deep is it down to the...
It's not deep, it's from 2 meters to 4 meters about. Yes, and would you like to come, you know?
Yeah, a good research project. I can help write application on that. That would be really good.
That sounds good, but I guess now I should pass the microphone on to somebody else.
Yeah, by the way, our department does a lot of marine archaeology, and also we're quite well connected with the rest of the NTNU, who therefore have access to a fair bit of geophysical equipment that's usually way out of our ordinary price range. We're talking autonomous submarine vehicles.
I know, I've been in contact with colleagues there.
It's your man.
Yeah.
Thanks for the lecture. Was very well. Many insights I got from this. I have a lot of questions actually. Let's start with. For 1 hectare, you're doing it by foot, or do you use also that trolley pulled kind of vehicle that you have shown?
We can do, let's go back to some pictures.
Yes.
With our radar, let's do it, it's actually, with this radar.
Yeah, for example, that one that you have shown also in the film.
Calculate around 2 hectares a day.
So you can make 2 hectares per day with that one.
Like this.
And if you only go by foot?
With this?
Yeah.
0.2 hectares. 2,500 square meters.
So you need 4 days basically for a hectare then?
Yeah, well, you do even, and this is, it takes about 45 minutes to connect it up, and then 30 minutes to connect it down, and then you'll do at least 2 hectares a day. You can do sometimes you can do a hectare quite easily, quite quickly. My record is 8 hectares a day.
Okay.
That was a long day, and that was fields that were like 4 meters square.
Okay.
With a magnetron, this is, it's not easy to see. This is like 16 of these sensors strapped behind an ATV. This is what we brought with us, that's now in Fiskars. With that you can drive at least 15 kilometers an hour. You can have an array that's 3.2 meters wide, and you can do at least 10 hectares a day in the field. But the costs aren't really associated with the data collection. It's the next phase, the data interpretation and writing the report and presenting the results. That's the most time consuming.
Sure. I understand. But this is the same with geophysics everywhere.
Yeah.
So in this respect, you are not alone with the GPR that you are using. How deep can you measure actually?
It depends on, of course, with the type of soil you're having. But if it's soil, if it's sand or gravel, and it's not dry desert conditions, but it's an ordinary Nordic field, I would expect somewhere between 2 and 4 meters, sometimes 5 or 6. But we don't need that. We need the top meter or two.
Well, I'm asking this specifically because I'm going to excavate a burial mound this summer.
Okay.
Yeah, in Bulgaria, and we are not yet sure how high it is, but I reckon certainly 2 meters, 3 meters. Last year we did one that was nearly 4 meters high. And of course, it would be very, very exciting to have a kind of a georadar scan before we actually start digging.
Yeah.
We tried this last year with the instrument that we had here in archaeology, but the results were not really convincing.
The mounds are difficult because if this is your mound, your signal goes into it
Yeah.
in various angles, and then you have to find a way to process all that. Also, the deeper the signal in the radar doesn't go straight down, it goes down like a cone. That means that the size of the cone in the bottom of it, let's say if it's a 200 megahertz antenna, the size of the footprint at 4 meters depth is, let's say 3-4 meters. That means that you can't distinguish features that are smaller than that.
Mhm.
Of course, if the signal goes very quickly through the ground, the cone is more narrow. If it goes really slow through the ground, it's very wide. So it depends on the material that you're having as well inside the mountain.
Mhm.
So even though you can see deep, that doesn't. The deeper it is, the lower the resolution is. So, like the stuff I showed from there, with a very, very good data set that shows very clearly stuff down to a meter or so, or even more. I wouldn't expect something like that.
Well, the ones that we are going to excavate will have no stones inside,
Okay.
Just soil, rather dry.
What you can, I'll show you examples of exactly something like this. Let's go online. We've done a geophysical survey over Norway's third largest burial mound.
Mm-hmm.
76 megawatts. And that's pretty fast internet. This thing.
Yeah.
This is just a part of it. I won an award for that picture actually. This is the mound. It's 68 meters in diameter and its preserved height is 6-7 meters. It has been somewhere between 9 and 12. And we did. This is the current preservation conditions. You have some very well preserved parts of it, and then you have some really mangled parts of it. And then you have some historical sources saying something about possible stone foundations or walls or whatnot. And we did radar.
Mm-hmm.
See the principles there. We did also earth resistance, with doing lines of electrical resistivity. So what I did, okay, I should flip this calendar up. There we go. So first I had the topographically corrected UPR section. Then I use a GIS to just kind of look at the most strong reflections, and then I did an interpretation of those where I kind of drew them up and simplified it a bit. Then you have what looks like bedrock coming in. You have the base of the mound. Is that line over there?
Mm-hmm.
That you see some places, not everywhere. And then you have some of the internal. So what we see then is that you have some lines that kind of follow the contour and some lines that doesn't, and then you can try and interpret that from a really perspective. We have layers that have, because you really have to expect some reflect like duplets on this ground surface. duplicates down. But if you look at the other ones that has a different angle and different direction, like these ones, they can tell you something about various phases on how the mound was built up, soil layers or things like this. So our interpretation of this is that it's a several phased construction as such.
But you couldn't see the burial itself, or with that?
We didn't find it.
Okay.
Or actually, we did in the central part. We had very high resistance from our resistivity, which is a different method than the radar, which is the topographical correction. This was really time-consuming to make. Depth sections, isosurfaces, and then we did have these. Which is the resistivity. So the red and the yellow bits have relatively high resistance. That means they're drier type of soils, sand, Belgian sand or something, or clay, or cultural layers or organic would probably have a lower resistance because the electricity moves through it. And you have this bit, for instance, sticking out in the center of the mound, which consists obviously of some kind of different material, which is more organic. So while this is very high, it could be like a possible central cairn or something. This is more organic and must be of some other material. And then you have the transition to the bedrock if it's stuff. And then you can look at the sections. I did. I'll go back to one here. I could do 3D modeling of the resistivity inside it and pick out threshold values in the areas that have low or high resistivity, like these blobs you can see there. You could also compare them, where you take your GPR section and compare it with your resistivity section, and then you have two different methods that measures roughly the same parameter, variations in electric conductivity. The only difference is obviously the resolution of it. And while radar is good to find the transitions between two layers, it doesn't necessarily say that much about the composition of the layer, while resistivity on the other hand says something about the composition of the layers, but it's not very good at finding the transitions. So the combination of those two, like here for instance, you have a lot of various moving directions of the transitions of layers in a relatively low resistivity area. So you can combine them and try to make sense out of it all. I'm not saying it's easy. Like this, where you have various layers coming in at different angles. Of course, Norwegian archaeologists are very, very occupied by Viking ships. They only find them in every big mound that they have. And it's difficult. I'm not even sure if it's possible. And we've done, well, I'm currently working on a report where we've used our 3D radar system with sections every 7.5 centimeters instead of what's usual for things like this, half meter or a meter, maybe even. This was done with a meters. That was probably 2 cores ago. But we're now trying to process a data set like this with a section every 7.5 centimeters through out a mound that's 50 meters in diameter and 5 meters high. It should be possible, but I'm still not sure how much we will get out of it in the end. And honestly, I'd rather do a thing on a flat piece of land than I'll do mounds because they're a bit of a pain to do. And it involves different software and a lot of processing work. And often the expectations of what you can get out of it is more than the actual gain, in my experience. But that might be me just looking at it from a wrong perspective. Mm-hmm. It's depending on your research questions and what you're interested in.
Sure.
But there are parallels and examples. People have done it, and there might be things there that could be of interest. I have quite a few articles on geophysics online, if you're interested.
Oh, yeah, I will have a look into it. I've seen you have it up on academia, so
Yeah,
okay, take a look.
there's an English abstract, and if you read in Swedish or Norwegian, then it will.
Yeah, in that combination it will work.
You can Google Translate that thing, and you'll still get something out of it, I guess.
Okay, many thanks. Who wants to have the mic next?
Right. I'm interested in bogs, or the places full of, full of water.
Yeah.
And are you working in that kind of places? And what are the risks?
I have not much experience doing things in bogs or in wet environments, but yeah, my colleague Kate Armstrong did a PhD on that in England, so I haven't had time to read it yet. I'm involved in a project with the National Museum in Copenhagen where they want to do attach various sensors to drones to investigate sites that are difficult to investigate in any other way. For instance, bogs. Again, I would, if I wanted to try a radar, for instance, I would wait until it's frozen and then go in winter time. And in Finland, that should be possible. Maybe not in southern Finland, but clearly up in north. But this winter it's been different than what we used to. That could be a way to go where you get more results. I've also seen where you have those earth resistivity things. I've seen that been done because in Ireland where they had some form of trackway built out of all twigs and leaves and wood, and they had an area that they were to excavate, and then they continued outside of it, and they wanted to see if they could track it that way. And they could by using electrical techniques, but then you have, it's quite slow, and then you have a series of sections that you do, and then you do a 3D model, basically like depth slicing afterwards. It's like a good idea I presented here. So there are things to try. The question is what type of archaeology would be in there? Is it distinguishable from, let's say, just a piece of wood, not archaeological piece of wood, a root system or something that made its way into the bog somehow? Can you distinguish the archaeology you're looking for from something that's just natural? How deep is it? What material is it? Does it have a magnetic contrast maybe? Is it stones put into the bog? What is it? Or is it maybe you can look at it from a different perspective and see, well, can I use geophysical methods to try and delineate an area of interest? Where, how big is the bog, how deep is it, different questions like this. That it might not find the actual archaeology, but it will help you understand its environment. That's a different perspective. That could also be fruitful if you look at it that way. So it depends on what you're interested in, I guess. But I would send you in the direction of Kate. Kate is also involved in cost action, and I'm sure she will be happy to respond.
Well, I have one practical question about your data, which is coming quite a lot when you are making measurements. And who is keeping this material, and is it possible to use somebody else than you yourself? Thank you.
Well, obviously, it's a lot of data. A site like Lechia, for instance, I think there was 50, that 2-hectare data set with all the fancy house bits. That's about 50 gigabytes of raw data. When you process that, that's 50 more. And then if you do a migration, which that's where I'll explain it. This is, I can't do that much. This is your antenna coming over a stone, let's say that. You're starting to, and the signal goes like a cone, so you're starting to hit it there. Then you go over it, and you start hitting on that side. So basically this gives you a signal like a U like this, because you're hitting it like that and then this and then like that again. So a stone object buried in the ground will be like a U. The shape of that U is dependent on the speed the signal goes through the ground. So if it's wide, the signal goes slow. If it's very pointy, the signal goes fast. But you can determine that to judge the speed of the signal through the ground and therefore also the depth to the feature. So a point feature, a stone as such, will look like a U, but you can collapse that U and migrate the data so it's more focused. And in theory also in high resolution. If you do that, you can change between the migrated data and the unmigrated data. The unmigrated, the raw data gives you actually a bit more information because you have just a point, but you know if it's a point source, if it's dipping, or what it is. So being able to flip those two through those two gives you even more information. That's another duplicate of the data sets. Now you're up in 150 gigabytes. And if you make a stitch of the entire area, that's 20 gigabytes more. So suddenly it becomes a lot of data. But if you describe how it's processed and your metadata treatment for your report of it, you can just keep the raw data and then someone else can just do exactly what you did and get the same result. Some manufacturers have their own type of file system that only works with their software. So the question then is, should you also keep or should you store everything in some form of generic file type? That would probably be the most recommendable one, but then you might lose some information that's otherwise part of your particular system. For magnetics, it's relatively easy. You have your X and Y position where are you in the world, and you have your measurement and maybe even some height information. And then as long as you can import an X, Y, Z your position and your measurement, then anyone else can open that file and use it and process it in whatever manner you have in your software. So that's in those kind of data sets, it's easier because it's not three-dimensional as such. It's one measurement for one flat piece of ground. But for radar, you also have the depth dimension on top of it, which makes it a lot more complicated. What we do is that we have a server, which is then where we keep our raw data and then the description on how it's been processed in our reports. And that has been backed up by the university every night. So it's actually backed up on tape every night. Everything that's contained on that server. And we're now going to, it's more and more bigger demand for us to write data management plans where we describe how we keep the data, how it's preserved, who has access to it, and so on and so forth. But I would be very happy if someone came along and said, that data that you did from that report there, is possible to have a look at it because I'm interested in this and that. That would be almost like a compliment for us. So if our data has interest for someone else who wants to use it either in a different way or looking at different research questions or a different angle to it, I think that's positive. But not everyone might share my more liberal ideas of data sharing.
It's nice to hear what you think about it.
Some people are more this their stuff, but yeah, people are different.
Thank you.
Yes, thank you very much, Arne. It was very good lecture and mind-blowing pictures and videos you have shown us. So, yeah. Of course, we have been discussing about this earlier as well, but I think the important thing is to know, because in Finland geophysical methods are highly underused, especially in a larger scale. And it would have been like a turning point for you to be in contact with these Vienna colleagues from the Ludwig Boltzmann Institute. I'm interested to know, where did the initiative come for that contact? Did it come from Niku or?
The Ludwig, as far as I know, I've not worked. I worked with people from NICU and from the LBI, but I've not worked directly with LBI. But as far as I know, they were given a very large grant to establish the Ludwig Boltzmann Institute. But that doesn't only do geophysics, but it's involved in a lot of other sciences as well. But what they got was quite a lot of funds to put up a European network as such, and find usually very high-profile test sites, like Stonehenge was one of them. Why aim for something less? And there was a couple of sites in Sweden, like what was it?
King's Mound.
Uppsala maybe was part of it. What's it called? Utbåkra was one of them. And what's that trading town?
Birka.
Birka was part of it. For instance, they didn't have partners in Denmark then. They did a lot in England. There's partners in Austria, and then they did Carnuntum, a whole Roman town, city, large city. It's a small town, it's a city, it's massive. They did the entire Stone Age landscape with fantastic results. But I think the money initially came from the Austrian government, and then, as far as I know, I might be wrong, and then they first partners came in with some ideas and some funds and some work hours and some research money, and then probably they applied for a lot of external funding on top of that. They're very good at what they do, and they took existing equipment and they brought in some of the best geophysicists or data scientists to write software and processing algorithms and things like this. So they have their own software, but as far as I know, it's only accessible to people that are part of it. It's not something that's commercially accessible, which gives them kind of a head start when it comes to a lot of, because they can do a lot of very cool stuff. The good thing with the 3D radar system is that the software is very fast, very intuitive, and it's like right out of the box. Everyone can learn how to use it, and it's there. I'm very happy with the capabilities of that. I think if you don't have access to the LBI data processing suite, I don't know exactly what it's called, but you use commercially available GPR software, you would struggle with getting the same type of results with a standard kit. Typically pulse, let's say a Mirai radar or something like that. The radar is excellent, it's just a question of what to do next after you gather the data.
Yes, once more, thank you very much for coming here, and we will be continuing tomorrow in field.
Yeah.
I will now say this in Finnish. Eli huomenna on tarjolla sitten kenttäpäivä, eli tämmöinen demonstraatio Karjaalla. Kaikki ovat sinne tervetulleita. Kello 11 tavataan Karjaan ABC:n parkkipaikalla ja sitten mennään katsomaan Arnen tuomaa 3D-maatutkaa ja miten se käytännössä toimii. Ja aikaa on kaikenlaisille keskusteluille sitten myös, niin tervetuloa. Huomenna on luvattu ihan hyvää säätä myös. Pitäisi olla kuivaa, pilvistä, yöllä pikkupakkanen, että toivotaan, ettei pelto ole liian pehmeä. Saappaat mukaan joka tapauksessa. Kiitos kaikille. Thank you once more.
Arne, do you know if